Hi, my name is Jay Runkle, and welcome to the Exploring Aggregation Framework webinar. So today I'm going to give you a quick introduction to the MongoDB Aggregation Framework, and I'm going to do that by running through a live example of working with some U.S. Census data. Before I begin, feel free to type in any questions you may have in the chat box in the bottom left-hand corner. We do have some folks that are standing by to answer questions as I am speaking. And just in case you're wondering, I'm going to go through a number of examples with the aggregation framework in the slides today. We will be providing the slides via an email message that you will get at the end of the webinar. So just stay tuned after the webinar for the email message, and you'll be able to review the slides and download them. So with that, I am going to begin. So our agenda consists of 4 components today. First, I'm going to talk a little bit about analytics in MongoDB. Then we're going to jump into a quick introduction of the aggregation framework. And then the body of the talk will be a series of examples of showing how you can use the aggregation framework to perform analytics on U.S. Census data, and I'll show some live running examples as part of this. And then finally, I'll conclude with some options that are available with the aggregation framework. So most people, when they are introduced to MongoDB, very quickly get up to speed with the drivers and the ability to essentially create documents, read them, do updates, and things like that, leveraging the drivers, the find, the update, insert methods that the driver provides. But often they aren't aware that it is possible to do analytical type queries in MongoDB. So if you need to do dashboards, create charts, graphs, reports, you can do all the types of queries that you would need to drive those reports in terms of grouping data by values, doing counts, derive values, averages, sorts, totals, sums, things like that. And what we're going to do today is talk about how you can do those types of analytics in MongoDB. And the data set I'm going to use as an example throughout the talk is U.S. Census data. And I downloaded into MongoDB census data from 1990, 2000, and 2010. And what I want to show by the end of the talk is give you a feel for if somebody says to you, I need to produce a report that shows which U.S. division, a division is just a group of U.S. states, has the fastest growing population density, and I only want you to include states with more than 1 million people, and I only want you to include divisions with more than 100K square miles, that you can write that query in the aggregation framework. Now you could also write that query in Java or Python or Perl, whatever your programming language is, but there would be a lot more work and it wouldn't be as performant as running that query right on the database. So I'm going to show that today. So just a little bit of background on how the United States government organizes the states into regions and divisions, because that is going to be the way that we are going to use this information as part of our queries. So in the United States, the states are broken up into regions, West, Midwest, Northeast, and then South. And then each region is broken up into divisions. So we have the Pacific Division, which is just Washington, Oregon, and California. And we also have the Mountain Division, which is Montana, Idaho, Wyoming, etc. And those 2 divisions compose the Western region. So as you see as I go through the queries, we will be doing queries where we group data based upon divisions and regions and perform all sorts of analytics on those different groupings. So if you had to do a query like I was talking about where you were trying to understand how the population density of various divisions were changing over time, and you were doing this in SQL, you would probably write some complex select group by having query in SQL. And what I'm going to show you today is how you can do the similar types of queries in MongoDB. So I was just, in preparing for this talk, I was searching around and I came across this Dilbert cartoon, which I thought was perfectly appropriate for today's talk. I mean, the aggregation framework is really cool, it's really powerful, And that's really kind of the point of this Dilbert slide. I'll give you 5 seconds to finish reading it. Hopefully you get a chuckle out of it. So let's jump in and talk about what the aggregation framework is and what is an aggregation pipeline. So in the MongoDB aggregation framework, in order to create a query, you define a pipeline. And a pipeline is a sequence of processing steps where the input of the pipeline is a collection, and then each stage processes that collection, performs an operation on the collection, and then the output of that processing is the input to the next step. So the data, it's just kind of like the Unix pipes, where basically you're piping data from one program into another. In the aggregation framework, you're piping the data from one pipeline stage to the next. And there are pipeline stages that do filtering like match, or calculations like project, or groups like the $group, or sort like $sort. So there's a whole host of types of pipeline stages that are available to do different style of analytics. So here is just so you get a feel. Sometimes seeing words isn't enough, but a real example will help crystallize information for various people. Here is a very simple collection and a very simple aggregation pipeline. So what we have is a collection with 4 documents that contains orders from customers. So we've got, and each document has a customer ID, an amount, and a status. And our aggregation pipeline, you see it's operating on the orders collection. We're performing an aggregate, and this pipeline has 2 phases. It has a match phase and a group phase. In the match phase, we're going to take the input of the collection, and we're going to filter out only those documents that have status A. So this takes the match phase takes the same syntax for a query as a find command would. And when we run our documents through the match phase, you'll see that only the documents with status A are left for the purposes of processing this pipeline. And then we're going to do a $group, where we're going to group the documents based upon customer ID. So in this case, we are grouping the first 2 documents by the same, have the same customer ID, so they're grouped together. And then as we perform the grouping, we are going to perform a sum on the amount field. So at the end of this pipeline, what we'll have is 2 documents. One will have one document for customers A123 with the total of their orders, the sum of the 500 and the 250, and the second document for the other customer in our collection, which is B212. There are a number of different pipeline operators that are available, and I am going to touch on just about all of these in the presentation today. I'm not going to go into in-depth of all of the capabilities, but I want to give everybody a good feel for the types of processing that is possible in the aggregation framework. So what I'm going to do is I'm going to introduce all of these different operators by showing you live queries with the census data. So a little bit more about the census data that I've loaded. So the U.S. government has, gigabytes of data from the census that you can download from us.gov. But to make this presentation consumable and easy to understand, I just downloaded some data at the states level. So I have data for each of the 50 U.S. states. And for each state, I have its name, what region and division it belongs to. I also have some census data for 1990, 2000, and 2010. And included in that data is the population for each one of those years, the number of housing units available in each one of those states, so the number of homes basically and apartments, and then the number of homes and apartments that are actually occupied. So of the total number of housing units as well as the percentage of which were occupied. And I've essentially organized this in my document model where the census data is actually embedded in an array that has 3 values, one for 1990, one for 2000, and one for 2010. So let's take a look at what the sample document might look like. So here is what a document what looks like for California. I've got the state, I have the region, and I have an array for each that contains a subdocument for each of the 3 years. And you can see that for California, the total population was about 33 million plus in 2000, it was 37 million in 2010, and 29 million plus in 1990. So let's switch over and take a look at the data actually within an application. So what I'm going to do now is I am just going to execute a query, and just so you can see what the documents look like in MongoDB. Here is I just listing all of the documents in my collection. It's basically like what I showed you on the slide. You know, here's the name of the state, the region, the division. You can see the census data for the 3 years in the array, and also I also have some other information such as the number of square miles in the state of California, number of square kilometers. Also, I have the geospatial coordinates, the longitude and latitude of the geographic center of the state of California, and we'll use that later on. So that's kind of an idea of what the documents look like. Let's take a look. If I run a count on this actual collection, you'll see that there's actually 52 states. So it turns out that count is actually one of the features or one of the functions available and provided by the aggregation framework, where it just essentially totals up the number of documents in your collection. So some of you might be wondering, saying, well, I thought there were only, at least last time I took geography, there were only 50 US states. How come you have 52 documents in your collection? And one of the ways we can figure out why that is by looking at another function that's available in the aggregation framework called distinct. And distinct takes actually a field name and will give you all of the distinct values for that field name for the documents in the collection. So if I run distinct on the name field, you'll see that we get the name of all the US states, but there are actually 52, because we're starting at 0, so the last one is 51. But you'll notice that in my data set, Puerto Rico and District of Columbia are also classified as states from the perspective of the US government and the census. So that's why there's actually 52 states. So back to the slides a little bit. Let's start out. We're going to build these queries and make them more and more complex. So we kind of just learned how to do count. We learned how to get distinct values leveraging the aggregation framework. Let's actually create an aggregation pipeline query. So what I'm trying to do with this query here is find out the total amount of area in the US. So basically, if you sum up the area in square miles of all the states in the United States, how much area is that? And what is the average area of all the states? You notice I'm using the group operator that I talked about earlier. And in this case, we are grouping by null. So whenever you group by null, you're basically saying group all of the documents together. Just create one group and group them all together. So if I switch back to MongoDB and we take a look at that and we run that query, what you'll see is that the total area in the US is about 3.8 square million miles, and each state has an average of 73,000 square miles of area. So in general, the $group operator or pipeline stage, essentially you can specify what you want to group by. You can specify a field reference or like a null value to group everything. And then within the group, there are various types of calculations that you can perform as you are doing the grouping. So you can do average and sum, which I just showed, but you can also do min and max. There are collection operators, so that if you want to collect all of the states as you're doing the grouping in each group, you can do that. And there's two ways you can collect them. Add to set will essentially ensure that you create a set. There's only one unique value. Or you can use push, which will just continually add the new values to the end of the array. And then first and last are special operators that assume that the group that you've created is sorted in some way, and they will enable you to retrieve the first member of the group or the last member of the group. So let's do a little bit more complex grouping, where now instead of grouping the entire data set into one group, we are going to group the the census data by region, and we're going to calculate the total area and average area just like before, but we're going to do it per region. And also, as we're doing that, we're going to count up the number of states. That's what we're essentially, every time we see a state, we're going to add one. And then we're also going to collect the state names. And I was able to use push in this case because I know that I have a document for each state and the states that are unique, so there's no need to use add to set. Let's go ahead and take a look at that particular query. And I'm going to run that. And what you'll see now when I perform that query, you'll see that the first region that's returned, at least the ones besides Puerto Rico and District of Columbia, is the Northeast. We've calculated its total area, about 181,000 square miles. It's the average area, each state is about 20 square miles. There are 9 states in the region, and here's the list of the states. And similarly, in the Midwest, those states are significantly bigger, shown by the total and average area. There are 12 states in that region, and there are the list of the 12 states in the region. So the way this works under the covers is essentially what I have here on the left-hand side is a very simplified version of my census data collection. I have 3 states: New York with an average area in square miles and what region it belongs to, New Jersey, its area and region, and California, its area and region. And then we do the group and we calculate the average area. So what that means is what MongoDB does is finds all of the documents that belong to the Northeast region, performs the average, and adds that number to the average area field, and then finds all of the documents in the Western region, performs the average, and adds that field to the average area region. Similarly, for calculating the total area and the number of states, it's the same type of operation where we're going to again group by region. For the total area, we're going to sum up the area M field by region, and that's how the total area calculation is calculated. And then for the sum, this sum:1, that basically means add a 1 to the value of this field for every document that belongs in that particular grouping. And that's how we end up with a number 2 for Northeast and a 1 for West. So let's take a look at another type of query. Let's say we want to calculate the total population in the U.S. by year. So we want the population in the U.S. for 1990. We want the population in the U.S. for 2000, and the population in the U.S. for 2010. So what happens is, in this scenario, we have a little bit of a challenge because we can't group by data that's embedded in an array. So what we need to do is we need to do an unwind step. The unwind step will make a copy of the document for each value of the array. So I have 50 documents. Each document has 3 subdocuments for the census data for 3 years. So that will I will end up with 150 documents. So let me run the query, and then I'll show you how it works under the covers. So if I go back to MongoDB here, and we'll run here's the same query. We're going to do an unwind step, which will essentially remove the array from my document, the data array, and make a copy of the document for each value in the array. Then we'll do the group by the year. We're going to essentially group the data by the year, and then calculate the total population for each year. So let's go ahead and run that query. And what we get is we get the total population in the U.S. for 1990, we get it for 2000, and we get it for 2010. So how did that work under the covers? We essentially leveraged this unwind operator. And like I mentioned already, it will essentially, if you unwind on an array field, it will make a copy of the document for each value in that array. And the way that looks is something like this. Again, this is a simplified version of the data I'm running. But I've got my states, and I have census data, in this case 1990, 2000, and 2010 for New York, but for New Jersey I've got 1990 and 2000. For California I've got 4 years. When I do the unwind on the census field, the one with the array, what happens is I end up with 3 copies of the New York document because it has 3 values in the census field. I end up with 2 copies of the New Jersey document because there's 2 values in the census field. And I would end up with 4 copies of the California document because it has 4 values in the census field. So the unwind operator essentially enables you to expand out your documents by eliminating the array, and then you can then use something like a group to perform some calculations like I just did. So now let's say we just did the total population in the U.S. by year. What happens if we only want the total population of the southern states, the states in the South region? We want those totaled by year. You see what I've done now is I've added a match phase to the start of the previous aggregation query, and what this match phase will do will filter out only the documents I care about, in this case the ones from the southern states. So let's go ahead and run that query just so you can see that. So if we do southern, there's the same query I just showed in the slides. Essentially what we'll get is for each of the 3 years, just like before, the population of the southern states in 1990, in 2000, and 2010. So the way the match operator works, or the match pipeline stage works, is you give it a query just like you would to the find query, and it will filter out the set of documents that satisfy, or it will filter out the set of documents that don't satisfy that query. Important that you cannot use a where clause. You can't use any server-side JavaScript in the aggregation framework. So just to continue on with my example, if we had 3 states, New York, Oregon, and California, in our collection, and we issued a match pipeline stage with the region as West, the only 2 state documents that would be remaining at the end of that pipeline stage are the 2 that have the value of region for West, in this case Oregon and California. Now let's assume that we want to do something a little bit more complicated. We want to essentially see the change in population for the states between 1990 and 2010. Did the states grow in population, and by how much? So what this particular query does is adds a couple of new pipeline stages to our query. We're still going to do the unwind like we did before, but the next thing we're going to do is we're going to sort the data by year. And that will essentially ensure that when we go to do the grouping, the documents will be ordered by year. So all the documents with that for census of 1990 will be ahead of all of the documents for the census data of 2000, which will be ahead of all of the census data for 2010. And so actually, I just realized I forgot to run that query. Let me go ahead and run that query, and then I'll move on to the next part of this. So if I go and run this query, what you'll see is we get exactly as what you would expect. We have the population for each of the states in 1990 and 2010, and then we've calculated the delta between them. That's essentially what this subtract function does right here. Let me kind of drill in and explain a little bit more what's going on. So I talked about the sort. Once we've essentially within the aggregation framework, it provides sort, limit, and skip pipeline stages that work very similar to the sort, limit, and skip with a find command. Essentially, it takes the same syntax and works essentially the same way. Because I've sorted the data in the aggregation pipeline, I can now leverage first and last. And I know that for each state, since I'm grouping by state name, that its first document in that grouping is going to be the 1990 data, and the last document in the grouping is going to be the 2010 data. So by doing this sort and then group by state, I can grab the two particular data for the years I care about, essentially eliminate the data for 2000. And then, so essentially the first and last are very similar to push and add to set. They basically enable you to grab information out and assign it to field values within a group based upon the order of the documents in that group. And then the last new stage in this query is a project. And the project enables you to do calculations. And when you see a 0 value here, that doesn't mean set the underscore ID to 0. That means eliminate that field from the document. Where this dollar, when I'm doing this dollar underscore ID, that's basically saying giving the name field the value of the underscore ID field. Obviously, this subtract here is performing the calculation, and then the pop 1990 with the 1 and the pop 2010 with the 1 basically says include that field in the next pipeline stage. So the project stage essentially enables you to do intermediate calculations. Essentially enables you to remove information from your documents, calculate new values, rename them, just change the shape of your documents overall. So let's kind of drill into what a project does using my simplified example. If I have a collection with 2 states and I issue a project saying eliminate the underscore ID field but keep the pop 1990 and the pop 2010 fields, what I would end at the end of the project pipeline stage, I would end up with documents that look like this. Similarly, if we take those same 2 documents and I have a more complex project stage where basically I'm saying get rid of the underscore ID, get rid of the pop 1990, eliminate the pop 2010 fields, but add a new field called name that has the same value of underscore ID, and calculate a new field called delta, which is the subtraction of the pop 2010 field minus the pop 1990 field. And if you do that, you end up with those same 2 documents, but with a different set of fields, just a name and a change in population. And that's essentially how that query works in the aggregation framework. So I'm sure many of you know that MongoDB has a very powerful geospatial indexes that support a wide range of geospatial queries. And you can leverage that geospatial engine from within the aggregation framework. So let's say we wanted to know or understand how the number of people that are living within 500 kilometers of Memphis, Tennessee, how is that population set changing from 1990 to 2000 and 2010? So is it growing? Is it decreasing? So from the people who live relatively close, like within driving distance of Memphis, Tennessee, how is that population data set changing? So I'm going to go back and actually I need to show you that query. So let's take a look at that query. So here's what that query looks like. There we use a GeoNear pipeline stage, and in this case we're saying we want all documents that are essentially reference a point within 500,000 meters or 500 kilometers of Memphis, Tennessee, which has the longitude and latitude coordinates of 9035, roughly. I eliminated the decimal points. So this GeoNear phase is going to act as a filter, but the filter that's going to be applied is a geospatial query. Let's go ahead and run that query just so you can see what that looks like. So if we go ahead and run this geospatial query, and what you'll see now is we will get, for 1990, we have the list of states, and these are the list of states whose geographic center is within 500 kilometers of Memphis, Tennessee, and the total population for that set of states is about 22 million. And you can see in 2000 it's about 25 million, and in 2010 it's about 27 million. So this gives you, a way to do really powerful queries leveraging geospatial data that you may have in your data set. So essentially the GeoNear operator essentially enables you to filter documents based upon geospatial information. It requires a geospatial index, so you need to have a geospatial index on your collection. And one of the cool things is that I didn't use it in my particular query, but as the aggregation pipeline is filtering the documents, it will also perform a distance calculation, and it can add that to the resulting documents as well. So you could know for each one of the documents how close it is to the particular point you referenced, and then you could use that data in subsequent stages in the aggregation pipeline. So the example of the way this works is, in this case, I've got two states. Each has a center field with a GeoJSON point within it, and I have built a geospatial spherical index on this center field. And then if I execute a pipeline stage with this particular query, the only document that satisfies that query that will be left is Tennessee at the end of that calculation. Okay, so this is pretty cool. We've walked through a bunch of different examples here. And the way people have traditionally used the aggregation framework is that when you issue an aggregation query, you get a cursor to the aggregation results. This is similar to a find query. If you do a find query, you'll get a cursor to the set of documents that satisfy that find query. But one of the new capabilities that we added in MongoDB 2.6 is the ability to output the results of an aggregation query to a new collection. So in this case, I have that same geospatial query we just walked through, but I added a new pipeline stage with $out, which is the name of the collection that I want my result set to be written to. So if I go back to MongoDB, and I'll issue that query now. You see we have the $out. You'll see right now in my list of collections, there are only 4 collections in my census database. When I execute this query, you'll see we don't get any results back, but if I do a refresh over here, you'll now see that we have a new collection, and that new collection has the 3 documents in it from, for the data for 1990, 2000, and 2010. So the results were written to a collection. So this is kind of a way that you can either save the result set of an aggregation query so that it can be inspected by, it's persisted and inspected for a longer period of time. Or another potential use of the aggregation framework now is you can write a aggregation query that essentially transforms your document, that does an ETL or reshapes your document from one shape to another and writes them to a new collection. So like I talked about, the $out essentially enables you to save your results to a new collection, and essentially enables new aggregation uses where you can essentially do document transformations or ETL processes right from within MongoDB. So at the beginning of this talk, I basically posed the question about, can we write a query like this? Which U.S. division has the fastest growing population density, assuming that we only want to include states with more than 1 million people, and we only want to include divisions less than 100 square miles. So I basically, in the first 30, 35 minutes I've been talking, I've given you all of the tools to write that query. And just in case you can't type that fast, here is what that aggregation query looks like. And I'm not going to bore you with the details of all of this, details of how this query works, but you can see here's where we essentially ensure that our states have a total population of 1 million. Further down, there's another match where it filters out the regions that have less than 100,000 square miles and things like that. We're performing the population density calculations down here, and if I go back to MongoDB, and we run this query. Here's the same query already typed in. You can see what we get is for each of the U.S. Divisions, here's the name of the division, South Atlantic. We have its total population in 1990, its total population in 2010, its area in square miles, and then the density calculation, the number of people per square mile in 1990, the number of people per square mile in 2010, and then the change in population density. So basically, the region that has or the division that has the highest growth in population density from 1990 to 2010 is actually the South Atlantic. All right, so there's a couple of aggregation options that I think people should be aware of that are very useful. So in addition to creating a list of pipeline stages, the aggregate command also takes an optional argument, which is a set of options that you can give to the aggregation framework. The first listed here is explain, and explain works very similar to an explain on a find command. Essentially, it enables you to understand the performance profile of this particular aggregation query. What indexes are going to be leveraged, how many documents are going to be read from disk, all those types of things. So it really help you understand the cost, or in terms of computer resources to execute this particular query. The second option, called allow disk use, is really powerful when you need to run a very large, complex aggregation query on a large data set. So in MongoDB, it will dedicate 100 megabytes of memory to perform an aggregation query. And if your aggregation query requires more than 100 megabytes, you will get an error saying there's not enough memory available to perform the query unless you turn on allow disk use to true. When you set allow disk use to true, that tells MongoDB that it can use the disk to store the temporary working data, so that it can essentially expand the amount of space that it can use to process the query. So if you ever run into a situation in MongoDB 2.6 where you get an error message during an aggregation framework that you don't have enough memory, you can turn on allow disk use, and that query will continue leveraging the disk for temporary storage. Finally, there's also a cursor option, which will basically enable you to specify the size of the initial result that should be returned to your application. And this is kind of a way to performance tune your application. If you know that on the typical usage, your application is only going to look at the first 5 aggregation results, there's no need for MongoDB to spend a lot of energy calculating out to 100 aggregation results or what have you. You can just tell it, just return the first 5, and if I want more, I'll ask for them. So it is important to note that the aggregation framework works with sharding. One of the kind of design concepts of MongoDB is that all the essentially useful capabilities should work across sharding. And the way it works, you need to read this slide from the bottom up. If you execute an aggregation query, each of the individual shards will begin processing the pipeline stages in the aggregation query until it becomes necessary for all of the results to be aggregated together. Maybe you're doing a group or something like that. And then when that occurs, all of these shards will send their intermediate results to one of the other shards called the primary shard, and that shard will take the intermediate results from the various pipeline stages, and it will complete the processing on all of the data, then return it back to the MongoS, who will then return the result to the application. All right, so just to summarize today, I hope that everybody now who has been watching this webinar believes that they can do aggregation style queries in MongoDB. So the next time they have requirements for creating dashboards or charts or graphs or what have you, filter, sort, count averages or whatever, that they have nowhere to go to essentially implement those types of analytical style queries in MongoDB. And the aggregation framework is really useful for doing basic aggregation style queries like I showed today, creating ad hoc reports, real-time analytics, and as I mentioned, for essentially doing ETL processes by which you take a collection and process it, leveraging project and things like that to reshape the data so that you can convert the data into a format that's more useful to the application that you're using. All right, so you guys, if you're still paying attention, you have successfully made it through the Aggregation Framework webinar. So I'm going to quickly scroll through some of these questions and that are presented in the chat dialog box and answer them. And so somebody asked about what app am I using for executing the queries. That's actually a tool called RoboMongo. It is not a tool produced by MongoDB, but it is an open source tool that you can feel free to leverage. It is actually the environment that I go through, that I use kind of on a daily basis. But that's, there are many good ones out there. It's just happen the one I tend to prefer. Yeah, so somebody asked about some questions about the capabilities in the aggregation framework between 2.4 and 2.6. So most of what I showed today is available in the aggregation framework in 2.4. I think the geospatial features as well as things like $out and allowed disk usage were not available in 2.4. The other thing is in 2.4, the results of an aggregation query are returned as a single document. So you will get a single document back with a results field, and that results field will be an array that has all of your answers. In 2.6, we changed that to a cursor, and the advantage to a cursor is that you don't run into the 16 megabyte limit of a document. So I think you'll find the aggregation framework in 2.6 a little bit easier to work with, but most of what I did today will work fine in 2.4. Yeah, somebody asked if you can filter text to see if a string field contains a particular word. I don't believe that the text indexes are accessible from the aggregation framework today. Yeah, so somebody asked if they could run aggregation queries on large sharded collections, and the answer is absolutely. The performance of those queries are really going to depend on the query, as well as do you have the correct indexes set up to support those queries. So I think in some cases you will be able to do real-time queries, derive real-time dashboards leveraging the aggregation framework. But I could also envision really complex aggregation queries that would not be able to do in real time. So you just it's really like any MongoDB query. There certainly is the potential to have sub-second aggregation queries, but again, it's going to depend a lot on the data set and the query. Yeah, so somebody asked when you're doing an unwind and you have a large data set, so essentially, as I mentioned before, in the aggregation framework, it will allocate, so the aggregation queries are performed in memory, and it will allocate 100 megabytes of memory for your aggregation query. If you're unwinding data in a large collection, you will exceed that 100 megabytes. So the option there is to leverage the allowed disk use option when you run the query, and then that will enable MongoDB to store temporary results on disk. And in that case, it will be able to unwind that very large collection. There will be, because it will be going to disk, there will be some performance overhead in doing so. You can also leverage sharding. If you have many shards, each one of those, assuming the unwind is early on in your aggregation query before all the data needs to be sent to a single shard for final processing, you will have all of those, you basically have 100 megabytes on each shard. Yeah, so somebody just asked that same question. The maximum amount of memory given to an aggregation query is 100 megabytes per query. Obviously, you have many running in parallel. Each one will have 100 megabytes of RAM assigned to it. Somebody asked if they're running a aggregation query and one of the shards goes down. Well, then basically what would happen in just like any Mongo query, if you are running an aggregation query on a sharded cluster and one of the primaries goes down and the query was running on that primary, then the query will fail, and you would just essentially need to, as soon as you get the error message, retry it. And then if all went well, a new primary would be elected for that particular shard, and then the query would execute the second time. The allowed disk, answer another question, the allowed disk usage parameter is something that you set in your query. You do not need a DBA or a MongoDB administrator to turn on that option. Well, I think I don't see any new questions in the chat window, so I thank everybody for joining the webinar today. As soon as we end the webinar, you will see a survey pop up, and we'd really appreciate it if you would spend a few minutes and answer the survey. We take the feedback that you provide seriously, and we use that information to make future webinars better and more valuable.